Imagine you climb to the top of a tall building and you throw a ball at an angle like this. You throw it at 3 meters per second. That ball is being thrown to the right, but you're also throwing it upward. How fast is it moving to the right? We could use cosine to find out. Theta would be the angle right here at the x-axis. How fast is the ball moving upward? That's the red arrow. But instead of throwing it at this angle, maybe you throw it at a shallower angle. Or maybe you throw it at an even shallower angle. Or maybe you throw it at almost no angle at all. Look at the red arrows on the y-axis and look at the purple arrows on the x-axis. What do you notice? Now let me ask a question. If you throw the ball perfectly horizontally, how much of 3 meters per second is along the x-axis and how much is along the y-axis? The answer, all of it is on the x-axis and none is on the y-axis. So if you climb to the top of the building and you throw it horizontally, we know that the projectile doesn't slow down on the x-axis. Gravity pulls down, so it has the same x velocity the whole trip. Notice how the arrows don't get shorter or longer. What happens on the y-axis? Well, gravity accelerates the y velocity. So, you start at 0, but then you speed up. And notice how the y velocities increase in length. That shows the object speeds up as it falls downward. If we connect the x and y velocity, we get the resultant velocity at each moment, and that resultant velocity shows us that it's kind of angling down as it travels. Let's do the same thing, but now we're going to throw it at an angle. The ball goes up and it comes back down. Again, it's a projectile, so gravity is the only thing that acts. Which way does gravity pull? It pulls down, so nothing is acting on the x-axis. The ball has the exact same x velocity the whole time. What about the y-axis? Well, that does get affected by gravity. As it ascends, it slows down, and so you see the arrows getting shorter. At the top, the ball briefly stops. When it comes back down, it speeds up, so those vertical velocities have longer arrows. Again, the arrows shorten on the way up, which shows that the vertical velocity slows down. And then the y arrows get longer, which shows the y velocity speeds up as it goes back toward the ground. As before, we can connect the x and y velocities to get the resultant, or the two-dimensional velocity, at every moment. Let's recap. Here are the two scenarios. What's the difference? The initial velocity. On the left, all of vi is on the x-axis, and none of vi is on the y-axis. On the right, how much of vi is along the x-axis? This much. How much is along the y-axis? This much. We are going to describe these scenarios using equations. What equation applies to the x-axis? The equation for constant velocity. And what equations apply to the y-axis? The equations for constant acceleration due to gravity. Let's put those down on the right side too. Now let's fix the equations. How much of vi is on the x-axis? All of it. And how much of vi is on the y-axis? None of it. What about the right side? What is the x velocity? How much of vi is on the x-axis? Vi cos theta. And on the y-axis, here, how much of the initial velocity is actually along the y-axis? It's not all vi, it's only vi sine theta. when we make these replacements, this is what our equations look like. Whenever you solve problems with a projectile that is launched horizontally, that means all of the initial velocity is along the x-axis, and there is no initial velocity on the y. And whenever you solve problems with a projectile launched at an angle, that means vi cos theta is the amount on the x-axis. How much initial velocity is on the y? Vi sine theta.